Okay, let's start. Okay, welcome to the graduate level course about this numerical linear algebra. I'm Jaegol Chu, a professor at the computer science department. And yep. So let me start with some basic information about our course. So in this semester, this is our classroom. We have changed our the location of our classroom maybe 2 times, and I think the current room is final location. And then we will meet at 10:30 a.m. It's a Wednesday. Yeah, so once every week on Wednesday, and yeah, starting at 10:30, and then until around 1:15 p.m. Okay, and then we will have some break in the middle for about 10 to 15 minutes. And yeah, in case you visit me, yeah, my office is located in the building right next to this building, which is called this yeah, Wujang building, and my room number is 502. And for all the class materials and the homework and so on, we will use this blackboard. So this one is, the website is kulms.korea, ac.kr. So I posted a few class slides, including this intro to our class in this website. And I also sent an announcement email early this morning, yeah, about this final room location. So yeah, I mean, you should have received, I mean, you must have received the email from me already, yeah, only today. So if you haven't, yeah, please make sure to see this course at this website by logging in with your credentials. And yeah, this is the graduate level linear algebra course. So I assume you have a solid background on this undergrad level linear algebra. Okay. So I listed some of the topics that I assume that you know about. So yeah. So linear systems and linear transformations, and matrix inverse and subspace, and as one of the first matrix factorization that you might have learned, which is called this LU factorization, and also this orthogonality, and also yeah, inner product and Gram-Schmidt process and least squares. Okay, and then this eigen decomposition is also quite widely used technique. So I assume that you have some yeah, fair amount of background on this eigenvalue and eigenvectors and so on. Okay, and these are some useful books. So and yes, oops. Okay, these are the same books, and if you haven't studied this enough about this linear algebra, I mean at an undergrad level, and then I suggest you to check out these video lectures and study on your catch up these materials as soon as possible, but not all of them, but you can maybe cover the first one, which is the most famous one, and I listed up some other linear algebra video lectures as well. And these are some of these topics that I will cover during our semester. So I will cover in the first phase of our course. I will discuss in more detail about this singular value decomposition, and then including the key theorems that is built on this that this singular value decomposition is built on, which is called spectral theorem. Okay. And then I think many of you may already know about this QR factorization, mainly based on this Gram-Schmidt process. Finding out orthogonal basis vector one by one given a set of vectors that are maybe just linearly independent but not yet orthogonal. But we will study a few other techniques to perform this QR decomposition. So that is called this Householder transformational reflection and Gibbons rotation and so on. So this is mainly about this orthogonality, and also about this orthogonal projections. So you guys will have some good kind of sense about the geometry frequently used in this linear algebra. Some sense about the high dimensional space, and then maybe projecting onto a particular direction or subspace and so on. Okay. And as we can see, this reflection is literally reflecting some point with respect to some hyperplane. So for example, suppose you have like this line, and then you are given this point, and then you can think of their orthogonal reflection over here, right? So this kind of operation or transformation, and then Gibbons rotation. This rotation is mainly rotating your given point to with some angle, right? So in this case of the 2x2 transformation, or in two-dimensional space, I believe you guys know the formula for this rotation matrix, which is where do we put minus or negative sign here? On top right? Is it correct? Right? So given the x comma y, and then the resulting vector will be your rotated result of this point with the angle of theta. Okay, and do you guys know about the high dimensional generalization of this rotation matrix? So what will be the rotation matrix in maybe more than two dimensions? More than two-dimensional space. So we don't have an explicit formula for this, but in general, this is kind of this matrix is kind of orthogonal matrix. Okay, orthogonal matrix. Okay. So what is the definition of this orthogonal matrix? What's the definition of this orthogonal matrix?
All of the rows are orthogonal.
And I mean, yeah, that's one of the necessary condition, but not yet sufficient condition. So, yeah, first of all, for each of these concepts or some definitions around, in the linear algebra literature or context, you guys have to be aware of, I mean, in which matrix that definition is that definition makes sense. Okay, so when talking about the orthogonal matrix, so we only think of some special case, special type of a matrix, which is square matrix. Okay, just a square matrix. So in matrix there, matrix can be categorized into two categories, like square matrix and rectangular matrix. Although rectangular matrix contains square matrix. So square matrix is just a matrix that has the same number of rows and columns. For example, like 3 by 3. Okay. So when talking about this orthogonal matrix, we only think of this square matrix. So it doesn't make sense to discuss this orthogonal matrix in the case of a rectangular matrix. But before then we can think of kind of a weaker condition that can also be discussed for the rectangular matrix. So for example, like this. So this is a 4 by 3 matrix. So in this case, so the student mentioned as the part of the definition for the orthogonal matrix as being, so we can when given a matrix, we can consider their rows and also their columns as well, right? And then the student mentioned that those three columns, I mean those three rows should be orthogonal, right? What does that mean? Given a set of vectors, so in this case we consider rows, and so we have 3 rows like this, and then these 3 rows, I mean, you pick up any 2 of them and form a pair, and then consider their compute their inner product. So if their inner product is 0, and then they are orthogonal. They are orthogonal to each other, right? So for any given pair of given set of vectors, if their inner product is always 0, and then it means their cosine theta is 0, and thus they are orthogonal to each other. And so suppose we have a 1, 2, 3 on the first row, and then maybe 2, 1, and what will be this value? So we can simply compute this this value so that their inner product becomes 0. So it is like this value, right? Okay, then we can also find another rows. But anyways, so in this case, we can at least think of the matrix that has the orthogonal rows. Okay. But usually when discussing their orthogonality from the vectors contained in our matrix, we mainly think of it is more often the case to consider their columns rather than rows. Okay, so in this case, let's just consider their rows first, or mainly, and then in this matrix, then we can think of this 3 vectors in 4-dimensional space, and then we can also think of their orthogonality, orthogonal set of vectors where any pair that you choose, their inner product should be 0. Okay, so this one is not yet the full definition of the orthogonal matrix. Okay, and then this is just described as a matrix. It's not an official term, but this is the matrix with the orthogonal columns. So we can safely say that about this matrix. But when thinking of the the definition of orthogonal matrix, then as I mentioned, it should be square matrix. So for example, maybe 4 by 4 or 3 by 3, and then we still consider their columns, and then they should be orthogonal to each other, and at the same time, what is the second condition that we have to satisfy? So it's a little tricky, but each vector length should be 1. Okay, so they are not only orthogonal to each other for any given pairs, but also when looking at each of these column vectors, and then their vector length should be 1.
This is not orthonormal?
Yeah, right. So so let me clarify that. So matrix, they can have matrix can have orthogonal columns, right? But the definition or the description that I just mentioned, being orthogonal to each other for any given pairs, and also their vector length should be 1. I mean, in that case, these vectors are called orthonormal, right? Orthonormal. So we can describe that matrix as being as having orthonormal columns, but but at this moment, this matrix can be rectangular matrix, right? So rectangular matrix can still have the orthonormal columns or orthogonal columns, but if it is a square matrix that has orthonormal columns, okay, and then there's a whole description. It's just called the orthogonal matrix. Okay, so that is just. So why is it not called the orthonormal matrix? I don't know. It's just the definition. Okay. So this whole description is the definition for orthogonal matrix. So first of all, it's a square matrix. Square matrix, and then it has to have orthonormal columns. So that is the definition of orthogonal matrix, and then that is also, I mean, so why do we talk about this orthogonal matrix? Because this rotation matrix is a special case of the orthogonal matrix. Okay, and actually you can think of they are actually equivalent to each other. Okay. Although in this case, I mean, in the case of three-dimensional rotation, it is a little difficult to define some rotation, because we can think of the angle, of course. So in the three-dimensional space, if we have a one single point here, and then it was rotated in this direction, for example, and then when thinking of their angle, so angle, of course, I mean, angle will definitely exist, but at the same time, the direction may vary as well. So the direction that this rotation follows can be like this direction or that direction or that direction and so on, right? So that way, yeah, you can see that it's a little tricky to define this the direction of an angle simultaneously with the amount of an angle, right? Anyways, so that is you can think of it as a kind of a generalized version of this rotation, in more than two-dimensional space. And and then how do we even so, how can we think of this rotation in a high-dimensional space in an easier manner? Okay, we can maybe slightly change our kind of a perspective of thinking of this angle. So have you guys studied about the standard matrix? Standard matrix. Does anyone know about the definition of the standard matrix? Where is it? Standard matrix. So, is there anyone that knows about the definition of this standard matrix? Okay, so let's think of this matrix transformation that we just discussed about this rotation operation. Okay, so we can think of this transformation of a vector defined by this matrix vector multiplication, and this is called the linear transformation. And it is it is saying this definition is a linear transformation, and so we are discussing linear algebra, right? And why do we study the matrix when we learn the linear algebra? What is the relationship between linearity and this matrix? Okay. So what's the connection between these two different things? So we can start with the definition of being linear, and so let's discuss the linear transformation, and then what's the condition or requirement to that this linear transformation should satisfy. What is the definition of being linear? Is it just a line? Okay.
Linear combination. Some variable is represented as linear combinations of other variables.
So that is the definition of a linear combination, right? That's true. Yeah. So that's the definition for being linear in the case of combining some variables or vectors or whatever elements, and then in the context of a transformation or functions, what's the linear transformation or linear functions? So it is something like this. So given x and y, no. So given the two inputs of an x1 and x2, and then we can think of the transformation of these two different input values, and then consider their y values, right? And then so we think of this linear transformation linear combinations of these two input variables. Okay, and then think of their function mapping or function output, and then that should be the same as the linear combination of these function output using the same linear combination coefficient. Okay, so that's the definition or the requirement of the linear transformation to satisfy. Okay, then here, so this is the this makes the connection between this linear transformation and kind of some function like really linear, shown as the line. So for example, suppose we are given this function, and then in the case of function, we first consider the domain and the codomain. So so what's the Korean term for domain and codomain in function? 도메인과 코도메인이 뭐죠? 네, 정의역 공역. 그다음에 그게 이제 도메인, 그다음에 코도메인이고요. What's the 치역은 뭐죠? 치역? Range?
Range.
Yeah, you're right. Yeah, range. So range is the translated word of 치역. Okay. Okay. So in this particular case, we consider the domain as one-dimensional vector or scalar value, and the output is also one-dimensional value, right? Or vector or scalar. Okay, and then is this function linear? Yeah, yes it is. And also we have to so that, I mean, in order for the function to be a linear function, this relationship or this requirement should be satisfied for any given values of a and b and x1 and x2, as long as x1 and x2 are belonging to our domain. So if our domain is the entire real numbers as a one-dimensional number, and then this should be satisfied all the time. Okay, so I'm not gonna give an example about this, but we can actually see this is a linear function. But what about this? Is this a linear or not? It is not, because let's just find some counter example. I mean, so there is no there is actually no no cases that that satisfies this, but x1 and x2 2, and then maybe a 3 and b 4. Okay, and then the function output is 5, and the function output is this, right? And then computing their linear combinations, and then so this is the result when doing the linear combination first of these two inputs, and then compute the mapping, right? But let's think. No, this one is corresponding to this case, right? And then what about this case? So we have to first do the linear combination between them. Then it's like 3 and 11, and then we just put it here, and then 35. Okay, am I correct? Okay, so these two are different, right? So this function is not a linear function. Okay, then still this function has also has the name. Okay, so that is a really close to linear function, except for this guy, right? So this bias term. Okay? So this if we remove this bias, and then it will become the linear function, right? So in that case, so those functions are called what?
Translation.
Translation?
It's a translation transformation. How you move it away from the origin.
Yeah. Yeah, so adding a bias can be, is also viewed as a translation, right? Moving it in parallel, right? So yeah, right. So translation, we can call it as translation. But at the same time, this transformation has also the name of affine transformation, right? So instead of being a linear transformation, it is called the affine transformation. Okay, then. So if you in the case of a deep learning literature, so we often use a fully connected layer and also convolutional layers, right? So all these both of these two layers can be viewed as this affine layer, because in the case of convolution we have a bias term, and also affine layer is not just a linear in terms of those inputs, but also it contains the bias term, right? So we mainly use the affine transformation in many applications, and then we can kind of do some trick to make this function as a linear function. So I mean that suppose you are given a affine transformation involving this bias term, and then we can change it into a linear transformation, okay, by doing some trick, and that trick is as follows. So if we have this, and then this is an affine transformation because of this term, right? And then we can represent it as this. So okay, so in this case, so you guys know that AX is a particular form of a linear function in the case of scalar kind of transformation. But now suppose our vector, our input or domain is not a one-dimensional, but a two-dimensional space. Okay, so in this case, what is the dimension of the codomain? It is one-dimensional value, right? So now this function was originally from one-dimensional to another one-dimensional space, but we changed it into this form, and then analogous to this, it can be viewed as this. Okay, some input which can be also a vector, and some scaling factor that is now defined as a matrix. Okay, so in this case we can check if that satisfies the linearity in the linear transformation. So so now if we have x1 as 1, x2 as 1, and then it is actually 1, 1, and then 2, 1. Okay. Then in this case, if we just use this linear combination coefficient, okay, and then computing their linear combinations, and then like this, right? And then if you compute this, with the inner product for the inner product with the this scaling vector of 3, 2, and then (48), which is the same as this guy, right? So here the real difference is this bias term has been also scaled together with this linear combination coefficient, right? So if your transformation is defined in this manner, and then it is still a it is now a linear transformation. Okay, and then also looking at this representation, it doesn't involve any bias term in this, right? So that way, the main affine transformation and the linear transformation has practically no difference, okay? Because we can just simply change affine transformation into a linear transformation by adding this bias term into a power of our input vector, and then now our transformation, although our transformation is defined, has the domain defined in a one more dimensional space. But anyways, okay, so this is the an example of a linear transformation. Okay, and now okay, now let me discuss briefly about the relationship between these linear transformation and maybe linear algebra. Linear transformation and maybe matrix transformation. The transformation defined by the matrix of an A times X. Okay, so in that case, suppose we have a transformation defined. Having the domain as R2 and the codomain as R3, and then let me give just the two clues. And the first clue is the function transformation of 1, 0, being it should be at least a 3-dimensional vector 1, 2, 3. It's just a hint that I give you. And then also suppose I gave you these two hints or two clues, and then also I'm gonna specify this transformation as being a linear transformation. Okay, so again, the hint or clue that we are given is that our function is linear, and then also we have these two particular function mapping, okay, of 1, 0 and 0, 1, and then using these clues, we can actually fully define, or we can obtain the full definition of our function. Okay, that is suppose you have an arbitrary input vector defined in our domain x1 and x2, and then it is always represented as a linear combination of 1, 0 and 0, 1, right? And then we know that because this function is linear, this guy is, let me see if I can copy that, paste it. Okay, oops. I think it takes longer than just writing it again. But I just wanted to use this high technology. Anyways, So this is the so the input is the linear combination of some vectors, and then because this is a linear function, and then we know x2 and x2 0 1, right? Okay, and then x1 times what? 1 2 3, and x2 times 6 4 5, right? So now we obtain the full definition of our function. Okay, so this is our full definition, but at the same time, it can be factored out as the matrix times vector. I mean product of a matrix of and a vector, and that is like okay. So this is represented as this. Okay, so yeah, you can verify easily that those two results are the same. And now, and also here, one of the widely used property of a matrix or matrix vector multiplication in the form of a column combination. So if we are given this matrix and the vector on the right, and then it can be viewed as the column, I mean linear combination of the given columns in our matrix on the left. Okay, so in this case, so these two x1, x2, x1 and x2 will work as a linear combination coefficient. Yeah, assigned to each of our columns contained in our matrix. Okay. So now this definition, I mean this is still a full definition, but at the same time we can represent it as a matrix vector multiplication, and thus we obtain the full definition as the form of matrix vector multiplication. So let's just review this example again. So we are given a few clues that our function is first our function is linear, and then we are just given these two mappings, okay, two mapping examples, and then we reconstructed the full definition of our function, okay. And then by looking at this definition of this function, yeah, it is represented as matrix and vector multiplication, and thus if our function has the domain and the codomain as some vector space, okay. So in general, like suppose your function is mapping m-dimensional vector into n-dimensional vector, and then in the case of an m-dimensional vector, yeah, so 1 0 0 and 0 and 0 1 0 and 0 and 0 0 and 1, right? So suppose you know the mapping of this finite number of input vectors, okay? Just an m-dimensional, I mean m different examples of function mappings, and then if your function is linear, and then suppose, I mean this function will have the function output as n-dimensional vector, right? N-dimensional vector, right? And that n-dimensional vector, I mean we will have m number of n-dimensional vector, right? Just like this case. So yeah, if our domain is two-dimensional and the codomain is three-dimensional, and then yeah, we can form this this kind of unit vector, I mean standard unit vector, I mean two different unit vectors, and then consider the function output, and that function output is just forming the column of our matrix vector product form of our function. Okay, so this is this matrix is called the standard matrix of a linear transformation. I mean when when dealing with the domain and the as long as the domain and the codomains are just a vector with the fixed or particular dimensions. Okay, and then if that transformation is linear, and then it is always represented as a matrix vector multiplication. And also, furthermore, like each columns of our matrix transformation, okay, and that each column is actually the output of just a standard unit vector of 1, 0, 0, 0, and 0, 1, 0, 0, 0, and 0, 0, 1, 0, 0, 0, and so on. Okay, so that way this matrix contains the output of the standard unit vector. I mean, these vectors are called the standard unit vectors, I think. Yeah, so we can just simply concatenate their individual function outputs, and then that will form the matrix in the full definition of matrix vector multiplication for the linear transformation. Any questions so far? Okay, then, so back to this rotation thing. So we can also think of this matrix vector multiplication as also being a linear transformation, and also we have these two columns, right? And then from what we studied in the previous slide, so the first column is the function output of 1, 0, and that is the function output. Second column is the function output of 0, 1, right? And then let's just verify that. So this definition, we know the effect of that transformation as rotating a vector with the amount of, I mean, the angle of an amount of theta. And then suppose our given input is this 1, 0, okay, 1, 0. And then if it was rotated by theta, and then suppose theta is 30 degree, and then it is something like this. So we have a theta here, and then because the length was 1, so here the length is also 1. And then what is the x and the y coordinates? And then x coordinate will be cosine theta, and y coordinate is sine theta, right? And then now let's consider another input as 0, 1. Okay, so if it is rotated, and then it will be rotated in this direction, and then we can also form this triangle, and that and then the coordinate of this point will be minus or negative sine theta and the cosine theta. Okay. Okay, so okay, so so this is so this is the main main things that you have to know about is the definition of the linear transformation and the standard matrix. And now so again, the connection between the linear algebra and the matrix thing, okay, is because the linear transformation is, linear transformation between vectors, okay, is always defined as matrix vector multiplication. So that's the connection between the linearity and the matrix. Okay, then okay, so back to this rotation thing, and then let's think of this rotation from another perspective. So that perspective is just rotating, not your point, not rotating your point, but rotating your axis. Okay, so in this case, if this point was rotated in this manner, so this point was rotated in this, and this, and in this is we know that this is an equivalent to having this x-axis. So x-axis is rotated in a negative direction as this, and this second axis is rotated into this direction. Okay. So in this case, it's a x old. So it's a y old axis, and this x new axis, and the y new axis. So given these two new axis or coordinate system, the same point. Okay. This same point was initially 1, 0, which is exactly on the x-axis, but because our x-axis was moved towards the clockwise manner with the amount of an angle of theta, and yeah, this point has the same effect of rotating it counterclockwise, right? So, so in this case, the rotation can be viewed as rotating your axis, okay, and orthogonal matrix, okay. Orthogonal matrix is actually viewed as this rotating your axis, and here if this axis was rotated here with the amount of negative theta, and if this axis was rotated into different angles, for example, okay, different angles. So for example, suppose we are given the point here, and then this axis was moved to like this, and the second axis was moved actually to this. Okay, so it's like this axis was moved and this axis was moved in this manner. And then what is the coordinate changes? I mean, what will be the new coordinates for this? Okay, so in this case, yeah, we have to think of our coordinates as kind of linear combinations. Okay, linear combinations. So yes, so yeah, it's a little bit going back and forth, but I hope you follow closely. You follow closely. But yeah, let's think again, or think in more detail about the coordinates. So what's the meaning of the coordinates? So for example, suppose we have a point as 3, 4. Okay, and then similar to what we did in the linear transformation, where we represented as this as 1, 0, 1, 0, 1 as a linear combination. Okay, so so in order to think of this linear combination of the vectors, let me just consider maybe this vector addition. So this vector addition is like, so we have a 2, 1 here, 2, 1, and 3, 4 over here. And then what's the geometric meaning of these vector addition? It is just forming this parallelogram and then finding out this another vertex of this parallelogram, right? And so this one can also be viewed as this kind of forming the parallelogram. But before forming the parallelogram, we first do the scalar multiple of these two vectors. So we have one vector over here, it's 1, 0, and then we scale it 3 times, right? So scalar multiple of a vector is just changing the length of vector, but not the direction, right? And then 1, 0, and then maybe this one is 3 times 0, 1, 4 times 1, 0, and then let's just form the parallelogram like this, okay? And then we always have this rectangle that has the angle over here as 90 degrees, right? Okay, so here, yes, so back to this example, yeah, by bringing that parallelogram thing to represent this coordinate of the given point, suppose now, let's suppose we are assigned these two new x's, and then maybe so this point is 1 0, and this point is 0 1. Okay, and then in order to obtain the coordinate of this point using the new two x's, then we have to form now this kind of parallelogram. Right? Okay, so so we need this vector, and then this is roughly like 4 times 1 0, right? And then so this is maybe 3 times 0 1, and then now using these new coordinates, I mean the new axis that we are assigned, the corresponding coordinate of this same exact point, okay, same exact point is now like 4, 3. Okay, and suppose when using this x-axis, this x and y axis, which looks just a standard one, and then we would have formed the parallelogram like this, and then suppose maybe 1 over here was a 1 0, and maybe this is a 0 1, and then the coordinate of this guy is like 2, 1, right? Because this guy is 2. I mean, the 2 times of this guy is the horizontal kind of line segment. And so using old coordinate or old axis, this was the point, and then this is the new coordinates of new coordinates by using the newly assigned axis. Okay, so this kind of thing that we just did is called change of basis. Okay, so this is also quite useful and widely used kind of tricks in the linear algebra. Okay, and this coordinate changing, coordinate changes are formulated as a linear system. Okay, linear system. So let's think of this problem in more detail. So I'm gonna give you just a single vector as maybe suppose the original point of this is 4, 3, which is represented as 4 times 1 0 and 3 times 0 1, right? And then suppose I gave you the two new axes, okay, two new axes, and then this point, okay, so this is the new axis, and then suppose this point was maybe 2 and negative 1, and then maybe let's see, this point, okay, corresponding to the new axis, and kind of point corresponding to 1 0 was maybe like this, although it looks like having the negative coordinates, but suppose these 2 points are the new 2 axes that you are assigned, okay, and then what are these numbers?
1 1.
So 1 1, but so yeah. So finding out this new coordinate value with respect to newly given axis, okay, newly given axis is equivalent to solving this kind of linear system, okay, where our variables are over here, and then we want to represent the original point by using the new 2 axis that has the like 1 0 as this point and maybe 0 1 as this point. Okay, so yeah, geometrically, so this point is fixed as like maybe, yeah, it's a little, yeah, it should be actually, yeah, I should use this 2 comma 1, okay, 2 comma 1. Okay, let me just change it a little bit because it might be a little confusing. So I want to make or build the example like this. Then it will be like this, right? Yeah, sorry, it's a little bit messy, but suppose you are given this point originally, which is this 2 comma 1, okay? And then it is really trivial, right? This is really trivial to decompose it into a linear combination of the standard basis vector of 1 0 and 0 1. And this kind of representation, yeah, it should be 2 and 1, right? This representation is geometrically corresponding to like this rectangle, right? Using 2 standard axes, 1 0 and 0 1. But what if we used the 2 new coordinates that has the new axis as this vector and this vector, okay? And in that case, what will be the coordinate values corresponding to these 2 linear combination coefficients, okay? So those 2 values will correspond to like the length, kind of a multiplier with respect to the new axis into this and maybe into this, okay? And then now we obtained, yeah, this new parallelogram, okay, for a given, still, yeah, still the same point is now represented as many different parallelogram depending on your given axis. Okay, so yeah, so what I wanted to point out in this example was, so in this case we have to mainly solve for these 2 values, okay, these 2 values, and then by just rewriting it, it is like 2 comma 1, and I'm just rewriting it literally, and negative 2 and maybe 3, yeah, and then maybe A and B and this, right? And then yeah, using the same trick, because these are the linear combinations of these 2 vectors, and like this, right? So now we suddenly obtained the linear system of AX equals B, where this is B and this is an A and this is an X, okay? So we can view this the process of solving the linear system as changing your coordinate systems, okay? Any questions so far? Yeah, and also, let me see. So I'm not sure how much we will use this. It's completely up to your, degree of your participation. But this is an online QA board where you can post your questions in real time. And then if you just enter, it's just a slido.com or slide.do. And then if you enter the code of, can you expect the code name?
NumericalAlgebra. KU NumericalAlgebra.
Yeah, you are almost correct. KU, and I don't like the long terms, so KULA, Kula. Yeah, so if you enter this Kula, then you will see this kind of board where you just post your questions, like, yeah. Okay, and then you can upvote on some of those previously posted questions. Okay. Someone actually voted, but anyways, if you are a little shy, like in asking the questions, or if I just keep going with my kind of explanations or description, and then you can just post your questions over here, and then I can maybe check this board from time to time, and then try to answer the questions. So any suggestions or questions will be welcome. Any questions about this question board? No? Okay. Okay, so okay, so we briefly discussed about this changes of a basis by assigning the new axis, and then obtaining the new coordinate values of the exact same point. The point, the position of this point, location of this point is still remaining the same, but your axis is changing, and thus their corresponding coordinates will also change. Okay, and then now let's get back to this standard matrix of a linear transformation. Okay, standard matrix. So in this case, so the standard matrix is just obtained by in the case of this rotation matrix, the standard matrix is just a concatenation of this rotated output of 1 0 and rotated output of 0 1, and then this output is this guy. Okay, and then now let's think of their angles and directions. So let's we do not talk about now we do not talk about this coordinate changes, getting a new axis, but we just get back to the standard matrix where those two mappings or two new points are just a function output of 1 0 and 0 1. Okay, so in that case, let's think of the new points and their relationship in terms of their angles and the distance. So what I mean is, suppose we are given these 2 points of 1 0 and here 0 1. Okay, and what were their angles? Their angle was, of course, 90 degrees, right, between the two specific input of standard unit vector of 1 0 and 0 1. Their angle was 1 0, the 90 degree, and their length is also individually their individual length was all ones, right? So this kind of special set of vectors of standard unit vectors of 1, 0, 0 and 0, 1, 0, 0 and so on. So they are or actually really the special case of an orthonormal set, where each vector length is all ones and their angle is 90 degrees for any given pairs, right? So that is probably the simplest set of orthonormal vector set. Okay, and then let's check if there are also normal relationships are preserved after doing this kind of transformation. So in that case, suppose, this guy was rotated into this point, right? And then, this guy is rotated into this point. Okay, and so, so we now have these two, so I'm running out of the colors. Let's see. Okay, let me just define. Okay, maybe purple. Okay, so we obtain those two vectors after transforming each of our standard unit vectors, and then let's just consider their lengths separately, and that length is all ones, right? And because their what is their theta, or the angle between the two? So they will also be like 90 degrees, right? 90 degrees, right? So this one is the properties of this rotation matrix. Okay, and then it's like so our class is working like a stack. So I'm getting deeper and deeper by following a new topic and the new topic and so on, and we are getting out, and then we now got out and then arrived back at the orthogonal matrix. And then you remember that I mentioned that. You remember that this orthogonal matrix is a generalization of a rotation matrix in a more than two-dimensional space, right? Two-dimensional space. Okay. So again, orthogonal matrix is the same thing as this rotation matrix in more than two-dimensional space. Okay. Okay. So here, what is what is really the meaning of this generalization? Okay. So what is generalized? Those conditions or those properties or those requirements are. If those requirements are still true, and then that can be viewed as the generalization of the rotation, which means that, in other words, you consider this set of standard unit vectors, and then consider their transformations. Okay, and those transformed vectors will all have unit lengths or the length of 1, and their angles are all 90 degrees. Okay, so orthogonal sets, even after we transformed each of the vectors in the orthogonal sets, and then the resulting vector set is orthogonal set if that condition is satisfied, and then we can think of that transformation as the generalization of the rotation in the more than two-dimensional space. Okay. Okay, now let's verify that is really the true in the case of the orthogonal matrix from the perspective of its definition. So what was the definition again of this orthogonal matrix? This guy, square matrix and orthonormal columns. And square matrix means, so if you have like this 4 by 4 matrix, and then from the perspective of transformation, then it will take the 4-dimensional input vector. So we basically think of this matrix transformation defined by A times X. Okay, and then what is the dimension of an X, the vector of an X and Y? They are both 4-dimensional vectors. So it's like from 4-dimensional space into 4-dimensional space. So if we have this square matrix, and then the dimension of the domain and the codomain will be the same, right? Okay, now we also consider this standard unit vector of 1, 0, 0, 1, 0, 0, 0, and 0, 1, 0, 0, and so on, right? And then what would be their respective transformation output in the case of the orthogonal matrix of this A. Okay? So we know that. So if we use the 1, 0, 0, 0, and then it's like picking up the first column and the second column and so on, right? And then initially 1, 0, 0, 0 and 0, 1, 0, 0 and 0, 0, 1, 0 and so on. They are also normal set, right? Their vector length is 1 and yeah. Okay, so individual column vectors included in our matrix will be actually the function output of these standard unit vectors, which are also normal set, and then their vector lengths should be remaining as 1 because these vectors are also normal. And also, what about their vector angle? Okay, so initially 1, 0, 0, 0 and 0, 1, 0, 0 and so on. They any pair among these vectors will have 90 degrees because they will just form this this kind of Euclidean kind of space, like where all the axes are orthogonal to each other, right? And so by definition of the orthogonal matrix, we know any given pairs will have the inner product of 0, right? So inner product being 0 means that their angle is 90 degrees because the cosine similarity or cosine theta is 0, right? Okay, so that way this orthogonal matrix, which is a square matrix and also normal columns. Okay, so in that case, standard unit vectors will all be, will all have the same length of 1, and then their angle is preserved as the 90 degrees. Okay. Any questions so far? So that's how we can describe this orthogonal matrix as just the generalization of the rotation. Okay. Angle is preserved and the length is preserved. Okay. Any questions? Okay, and then let me just add one more thing here. So we so far we only considered the unit. Some special and finite, only a small number of vectors that are just the special vectors of standard unit vectors. And for those standard unit vectors, the angle is preserved between them as the 90 degrees, and the length is also preserved as 1s, right? But that is actually, this angle and the length is all preserved for any given vectors, not just the standard unit vectors. So in the case of the orthogonal vectors, orthogonal matrix. So if you are given the orthogonal matrix and then you consider this transformation by that, defined by that matrix, and then suppose you are given the two vector x1 and x2. So for example, in the case of two-dimensional space, maybe you have 1, 2, and then maybe 4, 3. So you are given these two matrices, okay? So two input vectors. And then if your matrix A was an orthogonal matrix, okay, and then we can think of their transformation, right? And then the vector length of these two guys will be still the same as the vector length of the original vectors. And then we can also think of their angles between them, right? Between the two vectors. Any given two vectors, and then considering their angles, and these angles will also be preserved, okay? Yeah.
Do we have any break time?
Yes. But I'm just debating whether to finish the class early or having a break. Let's see. If you're fine with that, and then let me just continue for another maybe 10 or so minutes, and then finish today's class. Would that be fine? Okay. Yeah. Okay. So. Yeah, again, this orthogonal transformation is preserving the vector length and the angle for any given vectors. Okay. So does anyone, anyone prove that? Anyone can prove that? I mean, let me just give a kind of a spiritless. Insightless proof about it. So the proof is as follows. So given this vector x, and then we can think of this vector norm. So the double bar, okay, around the vector is denoting the vector length, just like the Euclidean length, right? So for example, like 3, 4 is 3 squared. And 4 squared, right? Okay, and then so this is represented as this because x is just a vector, not a scalar. And then if we consider this a squared version of this vector length, and then it can also be represented as this x transpose as x, because this guy is represented as 3, 4, and 3, 4, right? So that way, it's a really quite useful trick, because this norm operation cannot easily bring the vector inside out. Okay, so we can change this, right? And then let's consider this xa times x, and then consider their vector length. And then in this case, we have to take the square. And then it is represented as this, right? And then it is represented as x transpose, a transpose, a, and x, right? Because the transpose of a product of a matrix, they will change the order, right? So this is our result, right? And then the point is that in case A is a orthogonal matrix, and then A transpose A is identity, right? Identity. And so it will be just gone, and thus x transpose x, which is equal to x norm squared over x, okay? And then y is A transpose A being identity, okay? So you can easily compute, you can easily prove that, because it's really simple. So this is our A, and then we consider A transpose A, and then let's imagine the matrix on the left multiplied with this, okay? And then these column vectors are now our row vectors, right? Row vectors. Okay, so it's like this and this and this. And then let's just call this vector as A1, A2, A3 transpose, okay? And then this is our A transpose. And then we have 3 vectors, right? And then, so what is this value? What is this value? It is like this guy and this, right? So they are the inner product with the same vector, which is 1, right? And then what about the this value? So this value is like the inner product with the this and this, right? Okay, and then so it's like inner product between these 2 vectors, right? And thus they are orthogonal to each other by definition, right? So it's a 0. And so if you just use this properties, and then we can easily fill out this matrix as 1, 1, 1, and 0, 0, 0, 0, 0, right? So all the off-diagonal elements are the result of the inner product between the different orthogonal vectors. And then the diagonal entries are the result of the inner product with the same vector itself, right? And thus we can easily obtain like A transpose A equals identity matrix, right? In case A is an orthogonal matrix. Okay, so you guys know that, right? And then now let's think of this. Yeah, so we now proved that the vector length is preserved. And then how about vector angle being preserved? Okay, let's just also prove that. So in that case, in order to compute the vector length, we compute the inner product, like x transpose y, or it is represented as x dot y, because that is representing the inner product operation. And then now we consider this ax. We initially had an ax and x2, so x1 and x2, x1 and x2, and then now let's think of the inner product with this, and then it is like ax1 transpose and ax2 transpose. Oh no, this guy, right? And then we do the same trick here: x1 transpose, a transpose, a, and x2, right? And then we obtain identity here, and then x1 transpose x2, right? And thus the inner product is preserved, right? And then the inner product is represented as what? The length of an x1, length of an x2 times cosine theta, right? And then, yeah. Okay, so we have these two vectors, and if we represent their inner product as it is, and then it is like the length of an x1, the output of an x1 and x2 times cosine theta hat or theta prime, for example, right? And then let's just compare this guy and this guy, and then this guy, the length of an output vector of an x1 is the same as this guy. So this is what we preserved, what we proved over here, right? So basically, this guy is the same as the vector length of an x. Okay, so this guy is the same, and then, and then this guy and this guy is the same, and thus the remaining part should also be the same, right? So this guy and this guy are the same, and thus theta prime and theta is the same, right? So the angle is preserved, okay? Okay, so this is kind of insightless, like a proof. Okay, so we have no problem in just following these proof, right? But let's just have some kind of intuitive or kind of a little bit of a geometric understanding of why it should be true. Okay, so I think that is personally more important. Okay, so that is related to what I described as kind of a change of basis. Okay, change of basis. So, so here in this example, maybe like in this, maybe this example, if we rotate a rotation matrix or rotation transformation, is actually rather than rotating a point, it is actually the same as rotating the axis in a negative direction with the same amount of an angle, right? So in these cases, let's suppose all the points remain the same, but we actually change this angle, the first angle as this, and the second angle as this. Okay, so all the points are the same. The axes were moved, right? Axes were moved. So in this case, the axes are still 90 degrees because we rotated the axis with the same amount of an angle, right? And so it's like this is original or old coordinates or old axis, and then they were just rotated with the same amount of an angle, right? Okay, so in that case, this kind of rectangular kind of coordinate will all be the same, right? And thus their angles and lengths will be the same. So it's a little bit incomplete, but it's relying largely on our kind of intuition. but not fully detailed. But if we generalize this as the high dimensional rotation, where we have more than 2-dimensional space, okay, and then we would have originally like this kind of rectangular kind of coordinates where we have an x and y and z axis, and then this transformation by the orthogonal matrix, which is corresponding to high dimensional rotation, is like we move the first axis into, we actually rotate the first angle into some degree in a kind of some negative angle, okay, and then we also rotate the second and the third axis, the remaining axis, as some degree, okay, among the remaining space. So it's a little bit, I don't know, it's a little incomplete explanation, but you can think of this kind of rotation as kind of rotating in a negative direction. Rotating your axis in a negative direction, okay. And so if all the points are actually remaining, they are fixed and the axis were moved, and then from the rotated new axis, and then their new coordinates, if the axis were moved, and then all the points will be assigned the new coordinates, and their lengths and their angles will be preserved, as long as our vector sets or standard unit vectors, which correspond to our axis 1, 2, and the third axis, and then if each individual axis were moved into some direction and some length, and then if those new 3 axes are still kind of orthogonal to each other, and then the vector length is 1, and then all the points with respect to the new coordinate systems will have the same angles and the lengths. Okay. Not sure if it's a good explanation or not, but But anyways, we will discuss more on this high dimensional rotation when discussing kind of Gibbons rotation and house order reflection things and so on. Anyways, it's already more than 10 minutes. Anyways, so these are some intro about our class, and then these are some of these topics that we will cover. And one thing that I want to note is that if you, I feel I guess many students had the needs or feel some needs or have some motivations to take this class because you guys may feel that kind of lacking solid linear algebra background for maybe machine learning applications, including deep learning. Okay, but this class is basically graduate level course. Although it will really help because it can maybe give you the new research direction by just combining the new advanced linear algebraic techniques with the machine learning stuffs. But most of the topics that we will cover in this semester is basically at the graduate level. But most of the on the contrary, like most of the background necessary for properly understanding the machine learning and deep learning stuffs is just within the undergrad level linear algebra. Okay. Although we will cover some of them if I feel necessary, but but we will just discuss kind of a little bit more advanced topics that might not be directly related to machine learning or deep learning. So please note that. Okay, so we have a textbook on online slides, and then some grading policy is over here. And we have no projects, but you will have some homework and also both midterm and final exam. Okay? So this is basically just pencil and paper kind of a course. Okay, so any questions before ending our class? I'm not sure, but it could be Python or MATLAB. But I will not restrict particular language. Okay. Thank you very much.
수강 신청 기간 때 신청을 못했는데 신청하라고 할 수 있나요?
네, 할 수 있을 거예요. 여기를 방을 좀 여기 강의실을 그래서 좀 큰 걸로 바꿨거든요. 그래서 아마 여유가 있지 않을까.
아, 그래서 그냥 그 수강 전전 기간 때 해야 화사물질
아, 네네, 그렇죠. 정년 기간에 아마 하면 그냥 될 거예요.
네, 감사합니다. 스타트업에서 수업 들어봤는데 좀 수강 신청을 못했는데
아마 여유가 있어서 할 수 있을 거예요.
수업 시간에 필기하시는 혹시 올려주실 수 있나요?
네, 그럴게요. 이거를 내가 일반적으로 이거 강의를 다 이렇게 녹화를 해갖고 유튜브로도 올리고 하는데 강의 이거 PDF도 올려주도록 할게요.
필기하시는 거 보면서 복습하는 게
네.
뭔가 있을 것 같아요.
그렇습니다. 네.
하지만 좀 늦게 와서 출석.
아, 출석 안 했어요.
혹시 첨강식으로 들어?
네, 괜찮아요.
아,
네.